So the first thing I'll do is use the Lagrange interpolation to derive the shape functions for the U, or the axial degrees of freedom, and I'm going to assume that the element goes from 0 to L. Okay. So, like I said, we've done this so many times. All right, everybody okay with that? Then I'm going to use Hermite interpolation for the transverse degrees of freedom and the rotation. Those should all be Y's. So I just used Y instead of X here. Alright, so those same shape functions we developed many times. So now I'm going to develop each of those little stiffness matrices, submatrices. So the first one, K11, is actually no different than the regular stiffness matrix for a bar. So everybody okay with that? So for K12 now, we have EA over 2 times the derivative of W. All right, well, what's W? It's the degrees of freedom times its Wij, right? So the degrees of freedom for this problem are, for W anyway, they're what? W1, W1, theta 1, W2, theta 2, right? And then we're going to dot that into, because the dot product is the same thing as saying Wij. So it's just a summation of all the first terms added, second terms added, third terms. All right, so we're going to dot that into the shape functions for that, okay? And then we're going to take the derivative of the entire thing with respect to x, okay? And then we also have this so now this is going to be a 2 by 4. So I, which is going to be the rows, is going to go from 1 to 2, and J, which is going to be the columns, is going to go from 1 to 4. And we get that. Now you see, this is where it's different from anything we've done so far. Now the degrees of freedom themselves are actually showing up in the stiffness matrix. Okay? And I don't know, maybe it will help if we viewed these as matrices. So we have that one. And I have that one, so it's a 2 by 4. Okay? So then K22, I'm just actually going to, some of it's similar, so I'm going to rip this off. Okay. K22. This term now becomes squared. And then we have a whole nother integral term. It's EI. This is gone. And you have MM. 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 Yep, you're right. Thanks. Change those to second derivatives. And then go from 1 to 4. 1 to 4. There we go. Take a little while, and we'll get started on 2-1. There's EA. This is the same. Wow. D MM J D MM I. And then we're going to go from, this is going to be a 4 by 2, so we'll go from J equals 1 to 4, which will be the rows, and I 1 to 2, which will be the columns. Okay. And look at it in matrix form. All right. So then we can just, just for completeness, we can put it together. Constant array, zeros, 6 by 6, and then K, 1, 2, 1, 2 is equal to K. K, 2, 3, 4, 5, 6 is equal to K. This is 1, 1, 1, 2. Six, 1, 2, K, 2, 1. All right. So there's the whole thing. It goes off the page over here. Can't see it all, but it's a 6 by 6. But the thing to really, we kind of went too far to even bother putting it all together. But the point is that these degrees of freedom show up in the stiffness matrix. So we can't solve for those degrees of freedom by simply inverting it. It's not a linear system. So what do we do?